It was established in 1994 by a group of engineers, geotechnical engineers, civil engineers in Japan. And they're all outside, not in Nepal now. But I should appreciate that they tried to bring this Nepal Geotechnical Society. And Nepal Geotechnical Society is, it has a 10 to 15 years of very passive phase because of no activities. Starting from 2010 or 2011, we started doing like international conferences and international symposiums. And from last year, we started a few activities in the Nepal Geotechnical Society, like lectures and conferences. So we have a very big let's change this mic. Let's go. This is not good. Very good. So Nepal Geotechnical Society has 25 years of history. So this is the Silver Jubilee now. It was established on 18 May 1994, and that's why we decided to celebrate this Silver Jubilee on this day, Saturday, 18th May. And most of the members, founding members are, some of them are in USA, and some of them are in Thailand, some of them are still in Japan. So this is how we work. But in Nepal also, we had first president from Nepal, Professor Dr. Ram Krishna Ram. He is now in the US Harihad. And then next we had Professor Dr. Atal Bahadur Singh. And after that, in 2008, we had Engineer Tuklal Adhikari as the president. And I started serving for Nepal Geotechnical Society back in 2005 as a member, executive member. And then in 2008, I assisted Engineer Tuklal Adhikari as a vice president, then as the president from last year. So this is how we work. We have increased our activities recently, and I thank you all for your support and help to all of us, and I welcome you again. I hope we have about 4 to 5 hours of program today. Not only this memorial lecture, we have this Silver Jubilee celebration program from 4:30 p.m. today. And especially for this celebration program, we invited Vice President of ISS and GE for this lecture as well as for the Silver Jubilee program. I welcome Professor Singh to this program as well. Thank you very much.
We apologize for the recording interventions in the mic in the last session. Thank you very much, Professor Dr. Neta sir, for your welcome speech. And now I would like to request Chairman of this session, Mr. Sivanipal sir, to continue this session. Sivanipal sir.
Thank you, Andaji, Chairman of this Nepal Geotechnical Society, guests, Dr. Ishtu Singh, Dr. Tulada sir, and all the invitees who are present here. We have 2 memorial lectures and 1 promotional presentation. So I'll be requesting two promotional lectures. First, which will have 20 minutes of presentation, and one promotional presentation that is also of 20 minutes. After all the three presentations, then we'll have a short question and answer session. It's about 10 to 15 minutes. At the question and answer session, we'll be inviting all the presenters here. Then we'll close the this memorial lecture session. The first memorial lecture will be delivered by Professor Dr. Netra Prakash Bhandari. Dr. Bhandari is from Dang. He completed his bachelor's degree from Aligarh Muslim University, and he worked in Nepal Engineering College. Then he went to Japan for his master's and PhD degrees. He completed his PhD degree in 2003. Then he joined EMA University as an assistant professor in geotechnical engineering. Now he has been working as a professor of civil engineering in EMA University. He will be presenting lecture in creeping landslides. So I invite Dr. Bhandari to present his lectures. Thank you.
Thank you very much. We are sorry for this from here. I will be presenting from here. Thank you very much. I was planning to present a paper on recent developments in geotechnical engineering. This is my research topic, and I prefer to go to this because talking about geotechnical development, geotechnical engineering development is very relevant, but I thought it's like talking to you about geotechnical engineering is not really relevant today. Geotechnical engineering, it started to develop in 1930s and even before, and it started to develop from river dikes, levees, and embankments, and it was developed basically from the armies. Okay? So I know all of you are aware of all these strict historical developments of technology, geotechnical engineering. So I prefer to go with this because talking about the history is not really relevant today. History is very important, And in 1960s and 70s, what is going on now is like we are working with the same principles and theories, but with changing methodologies. So we use faster ways to analyze the problems and go with computer analysis, but we have all these theoretical things very similar to the theories we developed in 1960s and 70s. So we don't need to talk about all those histories and all those things, but the only thing is in 2000, in 21st century, what we are doing is we're developing computer analysis and all those analytical problems. We're going faster and faster, but theories remain the same. So that. And today I prefer to go with this understanding creep landslides. We are not very aware of creeping landslides in Nepal, but in Japan and in the world, it is a big problem in a sense like it doesn't devastate, it doesn't destroy you in a few seconds or in a few minutes, but it destroys your properties in about 10, 20 years or even 50 years, long time. So this is what I was working about in Japan. So the topic is understanding large-scale landslide displacement behavior through residual state creep shear tests in a modified creep shear machine. I don't know how many of you know the ring shear machine, because we don't use this in Nepal. Ring shear machine is it's a continuous shearing device. In direct shear, you have limitation of strain or displacement, but in ring shear, you can shear the material for infinite amount of the displacement. So one landslide may be like this. It is one example in my place in Japan. I see this. My place means Ehime. Ehime is a prefecture. Ehime University is a national university. The prefecture best name is Ehime University. So this is one landslide. It's a very huge landslide. The width of the landslide is about 2 kilometers. Length is about 2.2 or 2.3 kilometers. It's a very huge landslide and it creeps for a long time. It has been creeping for a long time, and the total displacement is measured to be about 2 or 3 meters in recent years. 20 to 30 years, it's 2 or 3 meters. So it creeps for a long time. Why it creeps, how it creeps is a very interesting topic for geotechnical engineers. So this is the boundary of landslide, and this is a map of Japan that shows the distribution of creeping landslides in all over the country. So black spots or black dots are the landslides. Japan is a mountainous country. We have about 83% mountains in Nepal. Japan has about 70%, so it's a very mountainous country. And when you have mountains, you have landslides there. So these are the creeping landslides in mountainous region. And it is like most large-scale or creeping landslides exhibit creeping displacement behavior. That is about, sometimes you have 1 centimeter to just a few centimeters of displacement in a year. It's a very slow-moving landslides. And these creeping landslides do not creep in a constant rate. They creep more in rainy seasons. They creep slowly in dry periods. So this is a graph that shows you the speed of landslides. And this is how you define creep. Creep is a phenomenon in where you have the constant stress. You don't have the changing loading pattern. You have constant stress, but with the time you have strain or you have displacement. And in creep, what we do is we divide the creep phase in 3 things. That is primary creep, secondary creep, and tertiary creep. When your problem goes into secondary creep, then it goes to failure. Somewhere with the time. It may be years, it may be minutes, it may be hours. So first creep, if you have primary creep and it doesn't go to secondary creep, you're going to have failure. But if it enters the secondary creep, then you have failure somewhere in a long time or short time. So this is a very fundamental graph indicating the creep behavior. And when you talk about landslides, you have this kind of primary creep and no displacement. Mandip? Zanaji? Point. This is your grip starts where after primary grip, your grip does not go further. So this is the end of grip. But with the season or with the change in stress, the grip starts again with primary and then constant. Primary and constant. So it is the different stages of grip. This way. This is a very basic behavior of landslide grip, one of the landslides in Japan. And when this is like it's not in failure state, it doesn't go into failure state, but you have cumulative displacement or strain. Okay? And this one is the grip behavior exhibiting primary grip, secondary grip, and then the tertiary grip. So it goes like, you have the failure. Ultimately, you have the failure. So in months or in years, you have this kind of flow. This is what is exhibited as the basic, the fundamental grip behavior by the landslides. And in ring shear machine, what we do is ring shear, we have in x-axis you have displacement, in y-axis you have the shear stress. What we do is we measure the shear strength of material in a way like it goes up to the peak, then starts coming down as this softening phase, and then goes to the constant state that is called residual state. We call this residual state, and this is the peak, pre-peak deformation, and then post-peak deformation. So we call this is the maximum strength exhibited by any soil material, but especially in clay materials, you have this after the peak strength, you have lesser amounts of shear strength, and when you go shearing or when you shear the material further and further, you will have constant strength after about 50 centimeters or 1 meters or even 10 meters in landslides. So you have this constant strength that is called residual shear strength. And in this particular research, what we do is how to define landslide creep in laboratory. So this is the main objective. In ring shear machine, what we do is we put the material inside, and this part is fixed. In this particular machine, what we do is the upper part is fixed, the lower part is rotating. It rotates like this. So this is the material, this pink part is the material, and it's a very small scale ring shear machine, and we have about 2 centimeters, 1 to 2 centimeters of material thickness. This is the cross section of this machine, and this is in creeping experiments. What you do is you apply constant loading here, and that constant loading rotates your machine like this at the bottom part of the machine. Okay, and so this is the exact scenario of ring shear creeping ring shear machine. That simulates the creeping behavior of landslides. What you do is you put the constant loading here, and this wire rotates your machine, the lower part of the machine, and this is constant, and we measure the strain here, displacement in this scale or whatever. We use some devices here. There is a laser device here to measure the distance between this point and this point, and that helps you measure the displacement of the machine, the shear. And this is the specimen, clay specimen It is about 10 to 12 millimeters, and the diameters are 80 and 120 millimeters. The outside is 120, inside is 180. So this is, the lower part is rotated, the upper part is fixed. And the results you obtain is like this. This is your time or displacement, and this is your shear strength. And this is the photograph of machine. And the results we have is like, it is the correction related, calibration related results. And what you do is you have pre-consolidation and then shear. So this is not really relevant here. Just skip it. And this is another methodology in shearing. You shear the material and go up to the peak, then it comes down, and in different stages you have re-shearing, stopping and shearing, stopping and shearing. So you have this method for understanding the peak. And we have to have some assumptions because nothing is perfect. The assumptions are at the residual state of shear, there is no influence of further displacement. That means if you go on shearing, you have large displacement. So we don't we don't really consider the influence of further displacement in soil material. And the amount of recovered shear strength if any, due to reduction in rate of shear, due to this state of no shear is negligible. And the effect on the shear resistance due to lack of uniformity in sample preparation, if any, effective stress application accuracy is negligible. And the change in the shear behavior due to changes in the value of RRCS. So this is residual state creep stress ratio. That means when your material is in residual state, it has the constant strength, but what you apply, like shear stress in creeping tests, so that is the ratio of the applied shear stress and the shear strength, RRCS. And there is no influence of any amount of displacement on the amount of shear resistance if sheared material has already reached this. That means because your material is already in residual state, so there will be no effect of any amount of displacement in that residual state. So any material has the same amount of shear strength in residual state. So that is the assumption. And these are the materials we use. So SP is sand powder, B is bentonite. We mix sand powder and bentonite. K is kaolin, and B is bentonite. So we have sand powder, kaolin, and bentonite. We use bentonite because landslide materials in Japan, in most cases we have smectite in the landslide slip surface material. And these are the physical properties. And these are the ring shear machine results, ring shear tests results. You have different materials, you have different residual state strength. Okay? So this is the sand powder. The highest one is sand powder, and the lowest one is the highest amount of bentonite. Like bentonite is 25%, kaolin is 75%, or bentonite is 25%, and sand powder is 75%. So these are the results, and these are the volumetric changes. So these are the tabulated results, the normal pressure and the peak strength, residual strength, and the volumetric changes, and the angle of shear resistance, internal shear resistance. And you can see kaolin 75% and bentonite 25% has the least strength. Okay? And sand powder has the highest strength. That is in terms of the residual shear, angle of residual shear resistance. That is only about 29. And for bentonite mix sample, it is 11. It's very low. And the results you obtain in creep test are like this. For a particular material, sand powder 100, you have time in the x-axis and the displacement in the y-axis. What happens is when you increase RRCS is residual state creep stress ratio. That is, if you have RRCS 1, then your material goes like this. It has a very long time, but it doesn't fail. Okay, it doesn't fail. This is the orange. It's not working. Okay. So this one is for the creep state that has no failure. But when you increase your RRCS from 1.005, that is only 0.5% increase. So you increase the ratio from 0.5% to 3%, only 3%. Okay. So your curves move towards left like this. And the ultimate failure, when you have 3% increase in the ratio of residual state creep stress, it fails within 30 seconds, only 30 seconds, okay? But when you have 1.005, just 0.5% increase in the stress ratio, it is about 100,000 or maybe 150,000 seconds. That's a long time. Okay? So these are the typical results of creep stress ratio, and these results are for. And the interesting thing here is you have the constant line here, and that is your material fails with the similar amount of displacement. Okay? So this is very interesting, in a sense like the material fails with the same amount of displacement. So we define this as delta C. Delta C is critical displacement. And this is all laboratory these are all laboratory results with different materials. And what you obtain finally is, so this is what we get like. And the mechanism should be, we have below the critical displacement, we have static state of friction, and after the critical displacement, you have dynamic, the effect of or influence of dynamic friction. So this is how we define critical displacement. And when you have a graph for residual friction phi r versus critical displacement, you get a straight line like this. That means when you increase you have stronger soils, you have less critical displacement. When you have weak soils, you have increased or greater displacement, critical displacement. And you have this kind of trend for residual creep stress ratio versus failure time. All lines are in the same trend. So these are the results, and so this is a model simulation with based on these experimental results. We get this kind of relationship between the time of failure is a function of RRCS and phi r. Phi r is the angle of internal friction in residual state. So these are and we use these results to model the behavior of material in creep state, shear strength of the material in creep state. And the concluding remarks may be like this. The displacement required for beginning of tertiary stress of creep for a particular clay material was found to be the same or constant for all sets of applied creep stress. And then in residual state of shear, our soil material shows creep behavior only under a shear stress greater than the residual friction resistance. What happens is when you have creeping behavior of materials, you have to apply the stress or the load less than the strength. But in creep residual state, you have to apply greater than the shear strength of the material. And the residual state of state creep behavior is exhibited up to a creep stress equivalent to about 30% greater than the residual. So it is like in residual state, you cannot go beyond. It's not 30%, it's 3% only. I'm sorry, it's a mistake. It's 3% only. So that is RRCS is less than 1.03. So this is the creep stress ratio, and this is only 3%, not 30%, 3% of the shear strength. And for a smaller residual friction angle, the amount of critical displacement delta C is larger, and vice versa. That is, this one is the result. So this one is the major result of this creep state, residual state creep shear test. And this is like we do these experiments to understand the landslide behavior, but applying this to the real field problem is not very easy. So we are still working on this issue, and we will continue working on this ring shear machines and residual state creep tests. And then thank you very much. Thank you.